does the LEV Foundation work on from a scientific point of view?
Right. So our flagship project is a is an ongoing program of mouse life extension experiments. And we're interested in rejuvenation, of course, in damage repair. So most of the interventions that we're looking at are of that nature. But because damage is very heterogeneous, there are many, many different types of damage. That means that we need many different types of therapy because each therapy works on a particular type of damage. And there's a fair amount of crosstalk between the types of damage, but broadly speaking, what I just said is true. So what we want to be looking at is combination therapies, where we apply a bunch of different things to mice at the same time. Furthermore, we want to be doing this with mice that are already in middle age before we've done anything at all to them, because that's, people will identify more with that than they will with mice that are treated from childhood. Um, and So we're just starting the first iteration of that thing right now with four interventions, four very different interventions that we're putting together in various combinations in mice at a contract research organization, which is actually a division of one of the companies that was spun out from SENS Research Foundation several years ago. So they're very much, mission focused. They're working very, very closely with us to make sure that costs are minimized and that everything's done really well. But it's still really expensive. This one experiment is costing $3 million. So that's really why people don't do these experiments. They just can't find the money. Luckily, I've been able over the years to build up a certain amount of credibility among people who have deep pockets, and so I've been able to bring in enough to be able to do this. But as I say, this is just the first iteration of what we want to be a rolling research program. We want to do round two of this starting in perhaps October. At the moment, we don't have the money for it. So I'm still out there very much beating the bushes.
So can you talk about the four interventions that you're planning for the first round?
Yes, absolutely. So, yes, this term robust mouse rejuvenation, I ought to first of all
Oh, yeah.
clarify exactly what I mean by that. Because around the same time that I coined the term longevity escape velocity, I realized that simply because mice age so much more rapidly than humans do, we'll never reach longevity escape velocity for mice. We won't be able to improve the therapies fast enough. But still, we can do stuff that will impress people. And so what I said is right. What we've got to do is take mice that are already in middle age. So that basically means 18 months old. These mice will have about 1 year left to live on average, and maybe year and three quarters maximum, something like that. And what we want to do is add a whole year to both of those numbers, so that they live on average to 3.5 rather than 2.5, and their maximum lifespan is maybe 4.25 rather than 3.25. And that's really hard, but the point is it's enough of an impressive result that it will allow my colleagues, even my colleagues who have reputations to worry about and jobs to keep and everything, to go out and say, yeah, you know what, we are within striking distance of getting rejuvenation to work comprehensively. And that will be enough to stop people from going out and saying, oh, aging is not a disease and it's like gravity and it's woven into the fabric of the universe and, we'll never be able to touch it with medicine. People will just not be able to do that anymore, which means that the floodgates will very much open. Oprah Winfrey will start taking notice, things like that. So that's why that's one of the reasons why we think it's really important to do this. Of course, the other reason is we may discover interventions that are translatable to humans. And of course, the track record of translating therapies from mice to humans isn't very good in medicine, but we have a feeling it might be better for damage repair than for the average drug for various reasons. So we'll see. However, you asked, what are the interventions that we are using in round one? So there are four of them. The first one is kind of a non-rejuvenation control. In other words, it's something that genuinely does slow aging down rather than reverse it. And that's called rapamycin. It's a drug that was discovered more than a decade ago now to have remarkably good longevity effects in mice, even when started late in life. And it's believed to work pretty much as what's called a calorie restriction mimetic. So that means that it basically tricks the body into thinking that it's in a famine when it isn't. It gets the body to be less good at using calories, especially in the case of rapamycin, using proteins in the diet. So that's one. Then we're looking at stem cell therapy. Now, there are various different types of stem cell therapy, but there's one type that has shown very impressive lifespan results, again, late onset in mice, and that is stem cells from young animals from their blood, from their bone marrow. So what you do is you mobilize, what's called mobilize, you essentially cause the stem cells in the old mouse to, at least a lot of them, to come out of the bone marrow into the bloodstream, and they leave basically gaps, places where, empty holes called niches, which is where cells can go back into. And then you inject a whole bunch of donor cells from the young mice, and some of the niches get occupied by these young donor cells instead of by re-engraftment of the old ones. And as I say, this has already been shown on its own, without combining it with anything else, to give a substantial increase in lifespan. So we were interested in that, and we're using that as one of our therapies. Then the third one is gene therapy for telomerase. So telomerase, of course, is an enzyme that's been very much in the news in terms of aging for many decades now. It's actually rather surprising that telomerase gives any benefit to mice, because mouse cells mostly make their own telomerase. And so you'd think, why give them some more? And this is not really completely understood even now, but it's somewhat understood. A group in Spain figured out that mouse telomeres are just really, really unstable, so that even though they are on average quite long, and they express, as I say, a lot of telomerase, nevertheless, a bit more telomerase is still beneficial. So again, that's been shown to have good effects on lifespan on its own. And then the fourth one is a senolytic. So, of course, senolytics are big news in aging these days. These are drugs that selectively kill cells that have got into this zombie state called senescence, where they are actively toxic. They're spewing out secreted molecules that are toxic to other cells nearby, or even to the whole body. And it's good to get rid of these cells. It was actually quite difficult to choose which senolytic to use, and the one we're using seems to have, because you want it to be very selective, you see, the one we're using seems to be pretty good in that regard. So those are the four things, yes, and we are dividing our 1,000 mice into 10 groups. So one group, of course, is a control group that gets none of these things, and another group gets all of them. And then we've got kind of baseline groups that get four groups that each get one of the therapies and not the others. So that kind of is to reproduce and recapitulate the published work on these individual therapies. And then we've also got groups that have 3 out of the 4, because we want to be sure to identify any case where there are interactions between these therapies that are actually antagonistic, where they kind of neutralize each other in some way. That's totally possible. So we want to know that.
Yes. Yeah, we have seen that elsewhere. So with the stem cells, is this going to work? So you're inputting from another animal. Is this going to work because the mice are very genetically the same?
That's exactly right. So the young mice that we're getting the cells from are of the same inbred strain, C57 Black 6, that the old mice that we're giving the cells to are from. So yes, there is no significant immune reaction from this.
Right. So translation would require some kind of way of dealing with that.
Yeah, we're not too worried about that. I mean, at the moment, of course, we do have this wonderful concept called induced pluripotency, where you can take cells from somebody and turn them into whatever you like, basically. And people have already got going on trying to make blood cells that way, so that you take cells from someone that needs blood, and you do this manipulation to them, and then you inject them back into the same person. That's called an autologous stem cell transplant. And it's not really ready for prime time yet, but it's fairly close, so we're not too worried about that.
Right. And I saw that you were planning to move to Het3 mice. Is it kind of next?
That's quite probable, yes. So Het3 is a 4-way cross. It's a strain that is made by taking 4 different inbred strains and crossing them together over 2 generations, so that you get mice with bits of chromosomes from each of the 4. And this was done in order to basically reintroduce hybrid vigor into these mouse strains, to get them to be resistant to things that to mutants maybe that have developed and become homozygous in each of the individual inbred strains. And sure enough, these mice do live a bit longer, and they're generally healthier than the inbred strains. So this 4-way cross was developed quite some years ago now, and is used as the standard strain by the National Institute of Aging's Interventions Testing Program, which is the same program that originally discovered that rapamycin works even if you start really late. It's tested a whole bunch of things over the years. It's been much less ambitious than what we're doing. They haven't done anything that involved injections, for example. They've done very little that involved even combining any therapies together. But still, it's a strain that's got a good track record. So we'd like to use it. However, as of now, you can't buy old Het3 mice. There's just people haven't been working with them in that way. Not in bulk anyway, not in large numbers the way we want them. And that's only going to be possible towards the end of this year. So we may very well switch to Het3 when we do round 2, but we couldn't do it for round 1 even if we wanted to.
Actually, right. I had a couple of questions on the technical stuff that I forgot to ask. So rapamycin and actually the Senolytic, are you planning to pulse them at all?
So in general, our approach, both for those two and for the other two, has been to figure out as close an adherence as possible to the best practice that's been seen in published literature by other groups. In other words, we look at the papers that have got the most impressive life extension results, and we just try to do exactly the same, even if we don't necessarily understand why it works, even if we suspect that there are certain variations that might do even better. We don't want to go that far in the first round. So in the case of rapamycin, there's quite a lot of experiments out there now. There are various different dosages, and we're using the dose that seems to have got the best results. Also, there are some studies that have just fed the rapamycin throughout the rest of the life. There's 1 or 2 studies which have only done it for a short period and then stopped. But the ones that have gone for the whole lifetime seem to have got more impressive results, so that's what we're doing this time. Similarly, for the Senolytic, and again, this is something that we may change in future experiments. But for the Senolytic at the moment, we basically just do one administration. Actually, it involves injecting the Senolytic 10 times over a period of a week or something like that, or maybe over 5 days. I forget now. But yeah, it's basically just one administration to get rid of the senescent cells, and then after that, of course, yes, the senescent cells may build up again. One thing that we have taken into account, though, is the fact that the order in which we do these things, in the cases where we are putting 3 or 4 of these interventions into the same mouse, may actually matter. For example, we've decided that we're going to put the telomerase in after the Senolytic. Why? Because we feel that there's a risk that the telomerase gene could somehow desenesce or partly desenesce some of the senescent cells, and those cells would become senescent again very quickly, but in the meantime, if we give them the Senolytic may not get to them because they've been desenesced temporarily. So we don't want to do that. Similarly, we feel that the presence of senescent cells might be somewhat inhibitory to the stem cells. So we are doing the Senolytic before we put the stem cells in, so that the stem cells have a nicely senescence-free environment in which to engraft.
In fact, the way that you divided the periods up is kind of non-classical in that you've decided it's like after a certain number of the treatment group have died. So could you talk about the tests that you're doing and the timing?
Yeah, so let me talk about the timing first, because this is something I'm quite pleased with myself about, because it's, as you say, it's a pretty new idea. I don't think anyone's done it before. And yet, everyone thinks, oh dear, why didn't we think of that? I'm getting very good reception for it. So yes, the idea is, in general, if you've got 2 things that you might measure during an experiment, and you know that those 2 things are going to be very highly correlated, why measure them both? You might as well just measure one. So in this case, the thing that's highly correlated is, on the one hand, lifespan, and on the other hand, healthspan, all the things that we might measure about the health of these mice. In other words, if we've got a therapy that actually works, and it extends the lifespan of these mice, right, whether it's a single therapy or a combination, and then we compare that with the controls, then at a given chronological age, we will expect that fewer of the treated mice will have died than the untreated mice. Fine. And we also expect that the various measures of health of these mice will be more useful in the treated mice than in the other mice. In other words, we know that those 2 things are going to be correlated. So In order to get a better, signal to noise ratio, what we're doing, instead of fixing particular chronological ages at which we test all our mice, instead of that, we are saying, okay, let's take each individual group of mice. We've got 20 groups because we've got 10 different combinations of treatments and two sexes, males and females. So for each of those 20 groups of 50 mice, we say, let's actually do our tests when 10 of the mice have died. I mean, of course, we do baseline before the experiment begins, and then we do the next test when 10 of the mice have died, which will, for a therapy that's working, that will be later chronologically than in the controls. But it means that if we compare those, then we would expect to be able to see which aspects of aging, which potentially life-threatening things, have been more affected by the therapies and which ones have been less affected. And we may get different results for different therapies. Similarly, we test at the next time point when another 8 mice have died, and so on. So we think that this is a big improvement on the way that these experiments have classically been done, and we're very hopeful that we'll be able to extract good information from that. All right, and so what things are we looking at? We're basically not innovating there at all. We're doing the standard things, as many as we can, that everybody does. So first of all, there's just visual things. There are certain aspects of aging which you can just extract quantitatively from photographs, like hair loss, alopecia, or curvature of the spine, kyphosis. These are two classical things that happen during mouse aging, and it's easy to do them that way. And there are other things that are also non-invasive, but they are behavioral rather than visual. So we've got tests of memory. There's something called the Novel Object Recognition Test, which has been very extensively used over the years. We're doing that. Well, various behavioral things, various physiological things. So grip strength, for example. You can, and there's something called the rotor rod, where you basically put the mouse on a spinning cylinder and see how fast you can spin it before it falls off. These are classical things that lots of people have used over the years, so we're not innovating there at all. And then there are things that come from blood draws. We are taking small amounts of blood and testing, the usual kinds of things that you'd expect. And then finally, we're actually killing some of the mice. Only about a quarter of them, because of course, when you've killed a mouse, you don't know how long it was going to live. But about a quarter of the mice will be culled at various time points in order to assess histology of organs, biological age in various other ways that you simply can't measure from the non-invasive approaches that I just listed before. Yeah, so again, the full gamut of stuff that other people would typically test.
Would you look at inflammation levels in the blood?
Yeah, so certainly, yes. We'll certainly be measuring things like, C-reactive protein, stuff, the kind of stuff that is typically measured in these things.
Are you going to do any epigenetic age tests as well?
Yeah, certainly. In fact, because epigenetic tests, methylation clock tests can be done on frozen tissue, we haven't actually needed to decide on a particular clock yet. And we're not quite sure how soon we will make that decision. But certainly, yeah, it's something that everyone's doing, so we're definitely going to do it.
Okay, it'll be interesting to see how well they correlate with your rejuvenation. Yeah. Okay. So what are you thinking for the next set of tests? You said you wanted to start some more in like October, if you can.
Yeah, I mean, that's definitely going to be subject to funding, but we believe that we'll be ready in October or so, subject to everything else. So yes, we're already starting to think about it, and if you look at the page on LEVF.org, the bottom section of it talks about our current thoughts in that regard. But this is still very much at the exploratory phase. Basically, my team and I will be spending April really, nailing that down, probably. Yeah, so basically things like, for example, we'd like to do a genetic senolytic, something in which you do gene therapy of some kind with something like a suicide gene under a P16 promoter, things like that. We're already talking to a group that's interested in supplying that to us. Then we're interested in plasma exchange. I'm sure you know that the revolution started by parabiosis experiments of the Rando lab back in the mid-2000s led to a lot of further work that was more realistically, clinically translatable. We at SENS Research Foundation funded the Convoy lab to do the initial work on plasma exchange, which was very successful. And that's moved on, of course, now to the idea of neutral blood exchange, where what you put in is not young plasma, but rather saline without albumin in it. There's still a bunch of questions I have about the extent to which the albumin is really the active ingredient. Just might be. But one way or another, this is definitely an important area, and it's kind of complementary to what we're doing this time around with blood stem cells. So again, we want to try that. Then we're also interested in partial reprogramming, because everybody is, right? And there are various ways in which we might go about that. But we're monitoring the literature very carefully at the moment, and also, of course, talking to people in the community before we make a decision about how we really want to go about doing that. So you get the idea. We've got quite a few options out there. I wouldn't be surprised if we also put in another, what I call a non-repair, non-rejuvenation control, because I think the logic of having rapamycin this time is pretty strong. The one that would be top of my list as of now is probably acarbose, which again has had very good results in the ITP and so on.
So are you planning to publish this in like a peer-reviewed journal? And any idea based on how long they're going to live? Do you think that would come out?
Right. So one of the enormous advantages that we have by virtue of being a non-profit that's independent and it's funded exclusively by philanthropy is that we don't have any of the pressures to, worrying about, priority or patentability or any of that bullshit. We can just say what we like when we like. So we're going to be putting out interim results very frequently. I'm aiming for once every couple of weeks from the beginning of the experiment. Survival curves on the website and everything like that, right? And absolutely, we would expect that we will publish various analyses. I'm quite sure it'll be the basis for a lot more than one paper in due course, but that's not our priority.
That would be very interesting, yes, to watch the way it moves. You're going to have a newsletter that we can sign up for?
Definitely. We already have a mailing list. We haven't really turned it into a newsletter yet. As you know, the foundation is very young, but yes, absolutely.
Have you thought about translation? Because at the moment, I mean, you're doing these combinations and they're drugs that other people own. So how would you take this and then put it into humans?
Yeah, I mean, this is something that's been on my mind ever since I really, realized that rejuvenation was the way to go. It was always always going to be a divide and conquer approach, which would involve the simultaneous application of a bunch of different things. Essentially, I feel that this, where there's a will, there's a way. So what I want to do is simply create the will. And that means showing that it works. If it works in mice, then there's a big incentive to find a way to make it work in humans, even if it does involve a whole bunch of tedious, cross-licensing of IP and this and that. At the moment, we're not even worried about whether something is patentable at all. Rapamycin isn't patentable, and that's fine as far as we're concerned. We just want to impress people.
I agree with you that if you can show that it will work, then people will find a way of making it available.